So I wanted to make a brief video to supplement your textbook about what a pi bond is. Okay, so you recall we've been talking about our two different types of bonds that we have in valence bond theory. Okay, and the first type is called a sigma bond. Okay, and so sigma bonds we get when we have orbital overlap, like you see here, and when that orbital overlap is along the axis between the two nuclei. So single bonds are sigma bonds, and they are formed between overlap between hybrid orbitals. Okay, and we talked about how to figure out what type of hybridization you have. So again, in more complex molecules, okay, what you'll have is you can have sigma bonds between different types of orbitals. So here, okay, we have a sigma bond between two sp3 hybridized orbitals in the carbon. Okay, but you'll recall that hydrogens, okay, just have s orbitals; they don't have p. And so when you have a sigma bond, a single bond between a carbon and a hydrogen, you have a sigma bond between an sp3 orbital on the carbon and the 1s orbital on the hydrogen. So that's that bond right there. Okay, so that's the kind of thing when you have different types of elements in your molecule. All right, so now we're going to talk about pi bonds. So what a pi bond is really is it's really the second bond in a double bond. So you can think of it that way, or the third bond in a triple bond. Okay, so just that the first our first single bond, okay, is going to be that sigma bond. So with pi bonds, okay, the way that they form is by overlap of parallel p orbitals. Okay, so these are not hybrid orbitals. Okay, so they're just your regular p orbitals. So they're not hybrid orbitals like you see in a sigma bond. Okay, and so the way they do it is they overlap kind of side by side. So this is kind of showing you the region of overlap. So this is what your electron density for your pi bond would look like. Okay, so here are your two orbitals, and when your atoms are close enough, they will overlap, and the electrons spend their time again in between the two p orbitals. Okay, so oops, this right here, okay, is your pi bond electron density. Okay, and so we typically think of them as being kind of above and below the plane of your atoms involved in the bond. And so when we have multiple bonds, okay, here's what we have. If it's a single bond, it's a sigma bond. If it's a double bond, it's one sigma bond and one pi bond. If it's triple, it's sigma and two pi bonds. Okay, and again, the sigma bonding is going to be just directly in line with the between the two atoms, and then the pi bond, okay, is going to be kind of above and below that. Okay, so that's the difference between sigma bonds and pi bonds. Okay, so here we can see it a little more realistically than what I scribbled on the previous slide, right? So we've got this, if we have ethene, so to remind you what the Lewis structure looks like, okay, we've got a double bond between the two carbons, okay? So the first of those two is our sigma bond, and that again is our sp3 hybrid orbitals, oops, as S1, 2, 3, nope, that's our sp2 orbital, sorry. Boop. That's an sp2 hybrid orbital. And then that second bond, okay, is the pi bond, and that is remember those carbons have electrons in p orbitals, and those p orbitals, okay, are going to be overlapping above, oops, and below your bond. I don't like the way that looks, so I'm just going to erase it. So when we look at that double bond as a whole, okay, what we see is we've got the sigma bond that really is just right between the atoms, and then the pi bond is above and below. And so this becomes important when you have in a lot of biologically relevant molecules, like the bases in DNA, where you have pi bonding that causes what we call base stacking. Okay, so base stacking is a consequence of the fact that we have pi bonds in our nucleic acid molecules. All right, and that's where I'm going to stop.